Hello everybody and welcome to day 28 of climate change. Last time we were together, we learned how the effects of climate change will impact different people differently, and we looked at some of the ethical dilemmas in addressing the problem. Today, we're going to take a look at what we can actually do about it. Come on along, let's learn about mitigation. Our quote for today comes from Pope Francis, the Bishop of Rome, who says, "The climate is a common good, belonging to all and meant for all." By the end of today, you'll be able to explain the components of climate change mitigation. Throughout the course, we have mentioned the existence of climate change mitigation, but we have not ever talked about what it actually takes to do it or what those strategies look like. So climate change mitigation is steps that we can take that will reduce the amount of climate change that occurs. This can be done primarily by reducing the amount of greenhouse gases in the atmosphere. This can be done by decreasing emissions or increasing sinks. We can kind of break this down into a couple different categories. We can look at strategies that increase energy efficiency, so not using energy we don't need, and using the energy that we do need to use really well. We can also look at strategies that decarbonize energy production. This is electricity production, transportation, and storage, how we heat our buildings, and how we move around. We can also look at land use strategies and other ideas for decoupling the economy and carbon. Energy conservation is any behavior that results in the use of less energy. This is the turning off the light strategy. When I turn off the lights when I leave the room, less energy is used and therefore less carbon enters the atmosphere. The most efficient kilowatt hour is the kilowatt hour not used. So our most efficient energy that we can use is energy we don't use. Drive your car less distance. Turn down the thermostat in winter. Turn it up in summer. Some of these actions, such as changing your light bulb, do not have a big impact on day-to-day life. Others, like driving less or turning down the thermostat, do. People do not like being asked to do things that they perceive as reducing the quality of their life.
In any season, a leaky home costs money. How do you stop it? It starts with a comprehensive home energy checkup. That's a series of tests and inspections to find out where your house could be more efficient. The end goal is to save energy, save money, and make your house more comfortable. Installing energy-efficient lighting and appliances will help. So will creating a sealed barrier around your house, kind of like putting a blanket around the outside, minimizing the leaks. Upgrading your home to save energy can put anywhere from 5 to 30% of your energy bill back in your pocket. Okay, to get a thorough home energy checkup, you'll need some help from a professional. Look for a home energy technician called an auditor in your area. Now, in this cold weather evaluation, the auditor starts on the outside, looking for problems around walls, joints, and under the eaves. If there's not a tight fit, you're losing energy and money. Next, the technician might head up to your attic to check for leaks on the top of your home barrier. That trap door could be a culprit, letting cold air pass into the house. A big part of the checkup is determining how well the insulation insulates. Insulation should be correctly installed in between all areas of the house frame. That means it needs to be evenly applied and not just jammed into spaces. And of course, if the insulation has fallen down, it's not working. Your energy auditor will inspect the holes where electrical lines pass through. If they're not sealed, they're leaking. Then it's down to the basement. Your furnace and water heater could be wasting energy. The auditor will check to see how energy efficient the furnace is. Furnaces generally lose efficiency as they get older, and it could cost you more to keep yours running than to replace it with a new one. Maybe all you need is a new filter. Some people haven't changed their filter for months, even years. That gunk clogging the filter means your furnace has to work harder to heat your home. If the water heater is several years old, it may not be efficient. And if it isn't insulated, it's also losing energy. Now it's on to the ductwork. The technician will inspect connections to make sure they make a tight fit. They have to be sealed to keep the warm air going where it's supposed to go. If the screwdriver can go in the hole, it means one thing for sure: money is going out. Now for the blower door test. The energy auditor will close all the windows and doors and anything else that lets outside air in. This special fan will depressurize the home. The idea is to suck air out of the house, allowing outside air to rush into the home through all those openings you didn't know about. Okay, so with the windows and doors closed and the fan running, leaks are easy to spot with an infrared camera. In winter, the auditor will scan the interior of the home looking for cold air rushing in. Here, the darker the color, the worse it is. These black spots mean one big air leak. It's an eye-opening experience. For this house, the recessed lighting fixtures are big problems. The auditor will also take a look at the kinds of light bulbs in those fixtures. If they're incandescents, they're using a lot of energy. Warm, compact fluorescents are an energy-saving alternative. So, the home energy assessment reveals ways that energy escapes your home, costing you money. The good news is, you'll have a comprehensive home energy report showing which efficiency upgrades are right for you and where to stop those pesky leaks.
So that's an example of a conservation strategy of using less energy that actually improves the quality of life. When you do not have cold air coming through your windows in the winter, you are more comfortable, you save money, and you use less carbon. In the 1970s, the United States had an energy crisis. We were unable to produce the energy that we needed, and OPEC was not supplying us with the oil that we were demanding. A number of steps were taken, one of which was President Carter instituting a thermostat control program. In the program, he stated that thermostats should not be set above 65 degrees in winter or below 78 degrees in the summer. This program saved 300,000 barrels of fuel daily. However, President Reagan abolished the plan because it was an excessive regulatory burden that was deeply unpopular. In the winter, put on a sweater. In the early 1970s, also in response to the energy crisis, President Nixon set highway speeds at 55 miles an hour across the country. Of course, speed limits are set at the state and local level. However, by tying federal highway funds to the plan, President Nixon was effectively able to set a national speed limit. The 55-mile-an-hour national speed limit was rescinded by President Clinton in the mid-1990s. Again, a strategy that was put in place to save energy, albeit not for climate change, was abandoned because it was unpopular by the people. While energy conservation is vitally important, it is not enough. Even if everyone drove a Prius, we would not be able to get our carbon emissions low enough. People used to say, just change your light bulbs, that'll fix the problem. And then there wasn't much of an effect. Very few people use incandescent light bulbs today. We have more efficient LED bulbs that better match natural sunlight, but even with that, we did not reduce our carbon emissions enough. Energy conservation alone is not going to do it. Well, if we can't look at energy conservation, we should look at energy consumption. In the United States, we're getting most of our energy demand from fossil fuels, coal, petroleum, and natural gas. Nuclear power and renewable energies make up a very small share. In our figure on the left, we're looking at energy consumption overall, so this includes transportation. If we look just at electricity, we can see that renewables and nuclear are composing only about 37% of our electricity production. If we want to reduce our carbon footprint, we need to increase the sector that's renewable energy or nuclear power, and we need to decrease the coal, petroleum, and natural gas sectors substantially. I do for a minute want to talk about coal. The argument for using coal is we've used it in the past. The infrastructure already exists. However, it is the dirtiest source of energy from a CO2 perspective, from a mercury perspective, and an aerosols perspective. It kills workers, and it kills people in the general population. It contaminates drinking water, it destroys mountains through strip mining, and it's expensive both directly and indirectly through health costs. The big switch we've seen recently from coal to natural gas had a huge impact on the amount of CO2 that we're putting into the atmosphere. It's also cleaner and cheaper. The downfall of coal is mostly the result of economic processes, not regulatory burden. Natural gas, which we oftentimes talk about as being a bridge fuel because it is cleaner than coal, it produces less CO2 than coal, it is still a non-renewable resource, it is still a fossil fuel, it still emits, and it does have some problems such as causing earthquakes and groundwater contamination when mined through hydraulic fracturing. The last non-renewable we are going to talk about is nuclear. Nuclear has a lot of arguments for it. It's a proven technology that produces baseload power without emitting carbon. And when we talk about baseload power, what we're talking about is the amount of electricity that we are constantly going to use. So the amount of electricity needed fluctuates throughout the day, from peaks in the afternoon to lows in the middle of the night. And ramping up and ramping down electricity production is very difficult for some sources of power generation. Nuclear is very good at providing steady amounts of energy over long periods of time. Nuclear power has actually released less radiation than coal, and it can be done on a large scale. Nuclear energy does attract controversy because it's expensive, but mostly because of the concern about radiation. What are we going to do with the radioactive waste? What do we do if something goes wrong? What about Fukushima, Chernobyl, and 3 Mile Island? And then we have the renewables. These are things like hydroelectric, wind, solar, and biomass. And we're not going to talk too much about each one of these in depth, but I do want to point out the advantages and disadvantages of some of them. So first, looking at hydroelectric, and this has the largest share of renewable energy that we are producing in the United States. And one of the advantages of it is it is able to produce consistent carbon-free power. The drawbacks of hydroelectric are impacts on wildlife, such as fish being unable to travel up rivers easily, even with fish ladders, dam failures, like we saw in Midland, Michigan in the spring of 2020, and the environmental impacts of constructing new hydroelectric dams. With wind, we have the advantages of them being cheap to run. Wind cannot run out. You cannot outsource the jobs of installation and maintenance. And it provides incomes to farmers because it's able to be placed in land that is actively being used to farm. Drawbacks of it are that some people think that it's unsightly. It kills birds, although not nearly as many as sources like coal does. And the wind does not always blow. With solar power, we can gain that from either photovoltaic cells or concentrated solar thermal power, which is cheap to run, it can't run out. And for photovoltaics, it's easy to distribute the power production across the grid. The drawbacks are some people think they're unsightly. And of course, the sun does not always shine. The advantages and disadvantages of burning biomass really depends upon the source. Are you burning trees? Are you burning foodstuffs? Are you burning agricultural waste? Are you burning landfill gas, methane that would have escaped from a landfill if you hadn't captured it and instead of converted into CO2, causing a reduction in the amount of CO2 equivalent in the atmosphere? Of course, some of these problems, they jump out at you. The wind does not always blow. The sun does not always shine in order to have net zero electricity production. And to do that, you need to have energy storage. And I know that we're all familiar with lithium-ion batteries, but those are not the only way that we can store energy. The most common way that we store energy at a utility scale is pumped hydroelectric. When you have pumped hydroelectric, when you produce extra electricity, so when the sun is shining or the wind is blowing, and you have extra electricity that's not being used, you take it and you pump water up from a low level to a high level. And then when you need that extra energy back out later, when the sun stops shining at night or when the wind stops blowing, you let that water that you pumped up flow back through the turbine. These are actually very efficient systems, and they've been proven in use since the early 1900s. The only drawbacks of these are the environmental concerns associated with building new reservoirs and the fact that you need to have very specific geologic formations in order to do this. It would be very difficult to build one of these out in the Great Plains where wind production is the highest. Used on a much smaller scale, so for example, we only have one major compressed air plant in the United States. So when you have extra electricity, you can use that to compress air into large underground storage. And then when you need that, you can let the air back out, and as the air is escaping, you can use it to power a turbine. These are very flexible. They have very responsive production, so you can increase and decrease electricity production very easily. However, you do need to have some place to store this. You have to store large volumes of air under very high pressure. And if you have changes in pressure, that impacts the voltage that you're able to produce. And then, of course, we have lithium-ion batteries, which you're all familiar with from your cell phones and laptops, which can go pretty much anywhere, even in houses and electric cars. They're efficient. However, there are environmental concerns associated with mining the raw materials, to cost, manufacturing, and recycling used batteries. From a purely economic perspective, There is a lot of money to be made by buying cheap electricity at low demand times and selling it at high demand times. Just to give you some ideas, that there are other energy storage solutions in the pipelines that are not necessarily being used at large scale, but are available, such as concentrated solar thermal, which I waffled a little bit as onto which slide to put this into. But the idea here is you take sunlight, you reflect it off of giant mirrors, and you use that to heat up some substance like a molten salt. And then you store that really hot liquid in insulated containers, and you use that heat later on. We can use block stacking, like in this case by Energy Vault, where when there's excess electricity, we use that to power a crane to lift a weight up and stack it on top of a pile, increasing its potential energy. And then when there's increased demand and lower production, you use the crane to drop that weight, and as the weight's coming down, that electric motor runs in reverse, generating electricity. Many different strategies like this exist. There's proposed solutions by using old mine shafts, using advanced rail energy storage, where you use extra energy to move weights on a railway up a hill, and then you let the cars run down the hill in order to get that electricity back. You've got energy storage in hydrogen. You can store energy and movement in flywheels. And you can use redox flow batteries, which have some advantages over lithium-ion batteries in their ability to be scaled. One of the next challenges is getting electricity where it's needed. Right? The sun always shines somewhere, the wind always blows somewhere, but it's not necessarily always here. If, for instance, you could put a solar project in the Saharan desert, you could power all of Europe. However, you need to connect Northern Africa to Europe in order to do something like that. The idea of a supergrid is the idea of connecting whole continents or the entire world together to send energy where it's needed. There are some difficulties associated with this, one of which is technological and the other is political. From a technological standpoint, when you try to transmit energy over long distances, you lose that energy to voltage drop. And so if we look at our typical electric grid, it runs on alternating current, but you cannot ship alternating current a long way. And so the idea is that you have a DC, a high voltage direct current backbone that moves electricity the long distances, and then it gets transformed into alternating current near the source. And you can do this in a couple different ways. All of them have their advantages and disadvantages, but the end result is still the same, where you can move that energy long distances. The Scandinavian peninsula is connected to mainland Europe by AC terminals and an independent DC grid. So they're using this option to connect mainland Europe and the Scandinavian peninsula. And then finally is politics. If you want to put a solar project in the Saharan desert in Africa and use the energy in Europe, the European Union and the countries in Northern Africa need to get along. They need to be able to make agreements, and they need to be able to stick to them. So we can transfer energy along. However, that does not necessarily make our system very efficient. If we want to make our system more efficient, we need to implement a smart grid. These result in fewer blackouts, more consistent energy demand. You get real-time pricing, which is a major boon for both smoothing out the peaks in energy demand as well as making electricity cheaper. It allows for better integration of wind and solar and better integration of customer owner power generation systems. So this is things like me putting a solar project on top of my house and selling extra electricity back to the grid.
Our current electric grid was conceived more than 100 years ago when electricity needs were simple. Power generation was localized and built around communities. Most homes had only small energy demands, such as a few light bulbs and a radio. The grid was designed for utilities to deliver electricity to consumers' homes and then bill them once a month. This limited one-way interaction makes it difficult for the grid to respond to the ever-changing and rising energy demands of the 21st century. The smart grid introduces a two-way dialogue where electricity and information can be exchanged between the utility and its customers. It's a developing network of communications, controls, computers, automation, and new technologies and tools working together to make the grid more efficient, more reliable, more secure, and greener. The smart grid enables newer technologies to be integrated, such as wind and solar energy production and plug-in electric vehicle charging. With our participation as informed consumers, the smart grid will replace the aging infrastructure of today's grid, and utilities can better communicate with us to help manage our electricity needs. The smart home communicates with the grid and enables consumers to manage their electricity usage. By measuring a home's electricity consumption more frequently through a smart meter, utilities can provide their customer with much better information to manage their electricity bills. Inside the smart home, a home area network, or HON, connects smart appliances, thermostats, and other electric devices to an energy management system. Smart appliances and devices will adjust their run schedule to reduce electricity demand on the grid at critical times and lower consumers' energy bills. These smart devices can be controlled and scheduled over the web or even a TV. Renewable resources, such as wind and solar, are a sustainable and growing source for electric power. However, renewable power sources are variable by nature and add complexity to normal grid operations. The smart grid provides the data and automation needed to enable solar panels and wind farms to put energy onto the grid and optimize its use. To keep up with constantly changing energy demands, utilities must turn power plants on and off depending on the amount of power needed at certain times of the day. The cost to deliver power depends on the time of day it is used. Electricity is more costly to deliver at peak times because additional, often less efficient power plants must be run to meet the higher demand. The smart grid will enable utilities to manage and moderate electricity usage with the cooperation of their customers, especially during peak demand times. As a result, utilities will be able to reduce their operating costs. By deferring electricity usage away from peak hours and having appliances and devices run at other times, electricity production is more evenly distributed throughout the day. The power being used right now was generated less than a second ago many miles away. At each instance, the amount of electricity generated must equal the consumption across the entire grid. Smart grid technologies provide detailed information that enables grid operators to see and manage electricity consumption in real time. This greater insight and control reduces outages and lowers the need for peak power. In control rooms across the grid, engineers will be able to more precisely and predictably manage electricity production, reducing the need to fire up costly secondary power plants. The distribution system routes power from the utility to residential and commercial customers through power lines, switches, and transformers. Utilities typically rely on complex power distribution schemes and manual switching to keep power flowing to their customers. Any break in this system caused by storms, bad weather, or sudden changes in electricity demand can lead to outages. The smart grid's distribution intelligence counters these energy fluctuations and outages by automatically identifying problems, then rerouting and restoring power delivery. Utilities can further use distribution intelligence to predict and manage electricity usage with the cooperation of their customers, leading to lower production costs. The charging of a plug-in electric vehicle can be managed over a home area network, or HON. The HON can balance the demand for electricity across the household and prioritize between the electric vehicle and other appliances to manage electricity usage and reduce costs. With smart grid technologies and consumer participation, utilities can more easily handle the increased demand for power to run the electric vehicles and ensure charging needs are met. By adding more plug-in electric vehicles to the grid, we have the potential to reduce fuel costs, lower our dependency on foreign oil, and help reduce greenhouse gas emissions.
So depending on who your electricity provider is, you can actually get a smart meter right now where they will charge you different rates depending on what time of the day you're using the electricity. If you charge your electric car at night, or you run your energy-intensive appliances at night, you both save money as well as make the grid more efficient. It's a win-win. Now, I know we just talked about supergrids, and so the idea of microgrids might seem like it's counterintuitive, but they're not mutually exclusive. Microgrids are a series of small portions of the electric grid that can connect or disconnect from the grid as needed. So we're not looking at separating ourselves entirely from other places. We're looking at the ability to separate ourselves if we need it. These provide security from outages, efficiency, and have been in use on college campuses and military bases for decades. These promote distributed or localized power production. When you have microgrids, that makes it much easier for individuals to be producing electricity and selling it to the grid than when we have a system where we have large areas all powered by individual plants. There is resistance by some utilities to distributed power production because that's putting the power to make money off of electricity production into the hands of someone other than themselves. When we look at microgrids gaining the ability to become independent when needed, you do look at the idea of needing local energy storage solutions. Microgrids must also be intelligent. At the end of the day, what you're looking at having is a large supergrid where you're able to transport energy from where it's produced to where it's needed, that is smart and is able to vary pricing in real time, which provides the opportunity for people to spend less money overall on their electricity, as well as encourages people to make energy use decisions that make the grid more efficient. And by distributing that power in microgrids, you gain the ability to resist power outages that cover long areas, as well as gain the opportunity to produce and store one's own electricity, which can be monetized. Reworking our aging electric grid will require significant investment. However, those will most definitely pay off in short order. So today we've taken our first look at some of the climate mitigation strategies, but there is so much more. Next time we come together, we're going to look at climate mitigation part 2, and we're going to learn about transportation and land use changes. I hope you all had a wonderful day and learned a lot. We'll talk to you all later. Bye-bye.